Okay, thank you. Hi everyone. So I'm here to present our work with Mihaela and Nicolas. So it's about an extension of separation logic to overlay data structure to represent everything. So first, let's talk about separation logic. So it is logic used to reason about programs, proof of programs. We use a specific primitive called separating conjunction to combine disjoint structure. We use it with a specific rule in a proof called the frame rule. It describes the fact that if I is not affected by the problem C, then we can compose it from both sides of the triple because the domain disjoints. So in SL, we want to specify data structures, and to do so, we use some fragments that are very expressive predicates, inductive predicates. So here are examples of inductive predicates. The first one describes an equivalent list. So we can see that there are two rules that define these predicates. Each time there are the first part defines the head of the list, and in the second rule, you can see that the tail of the list is separated from the head. We can also define binary trees, and we can define more complex data structures, such as this data structure that is called the tree with it. So our motivation is insanity result, because it's convenient theoretical result. So in separation logic, there are many results for disability. For instance, the satisfiability problem is decidable in various fragments, and in particular, a very expressive fragment called symbolic heaps that contains only the separating conjunction and not the magic bond, and that also contains inductive predicates. We can also find fragments where the entailment is decidable, such as the so-called easy fragment that adds some other conditions on the inductive predicates. But what we are interested in is overlay data structure, and that raises some issues because in the first place, separation logic is defined to combine disjoint structure and not structure that share some elements. So we have issues of expressivity. We still want to define structure inductively. We have issues of compositional reasoning. We still want to reason locally by composing the structure, and we want disability results for satisfiability and entailment, because it is what is useful in proof of program. So let's see an example of the kind of proof that we want to specify. So you can see here overlapping. There is a tree is defined in blue. We can define the tree in separation logic, for example, with a blue field, and there is also a list in pink. Can define list in separation logic with pink field, but we cannot compose them because you see they share all the elements. So we want to define a new field that allows to combine two structures if the fields are the same. And we also want to describe what part is shared. So to do this, we introduce a new kind of variable called set variables that will describe the part of the structure that are shared among the structures. So we introduce a new extension of separation logic that we call overlaid separation logic. The contribution of this article is first the introduction of this fragment that include all the issues that we saw previously. First, we still have inductive predicates, so we can define structures such as in separation logic. We have, like I said, new connective, the overlaid sparking conjunction that work kind of like the sparking conjunction, but it allows to combine structure if they use the same fields. And we prove the decidability of the satisfiability in this fragment, and for this we propose the decision procedure that leads to this theorem. So the satisfiability theorem is decidable for this extension in an H time if each predicate only allocates one field. So as we see in the example, can define a structure that uses one field to define a tree, a structure that uses one other field to define a list. But same predicate cannot use two these distinct fields in this definition. In this definition. So let's see the syntax of fragments. So we can recognize some elements of separation logic. I will detail this. First, we extend the semantics separation logic. So we still have a store that maps the variables to a location. We have a definite set of locations. We still have a heap, but this time the heap maps a location and a field in a couple of locations. So the heap is a partial function, and we add a set interpretation for our set variables. It maps the set variables to a set of locations. So the first setting is the empty atom. It's the atom that denotes the empty heap. The second atom is the points to atom. It is used to allocate variable. So here X is allocated. The difference with the separation logic is that we use field to allocate the variables. Here we say that X points to the total Y1 to Y2. It is satisfied if the heap corresponds. We have connective, so logic function in the classic disjunction. We have the separative conjunction. It is used to stand the fact that the two parts of the disjunction cannot allocate the same variable. And we have the overlaid separative conjunction that describes the fact that the two parts of the formula cannot allocate the same variable with the same field. We also have some equality constraints of the location, so addressing and non-addressing of the variable. Because we have set variables, we will add set constraints, for example, to state that two set variables are equal or one is a subset of the other. And we also add arithmetic constraints, for example, to talk about the cardinality of the set variable, if you want to define a list, for example. And finally, let's talk about inductive predicates. So inductive predicates are defined with a finite set of inductive rules. If we take all these rules, we have the set of inductive definitions that define all the predicates. We associate with each predicate a unique set variable that is passed as parameter. So this set variable is supposed to describe a subset of all the variables allocated by the group. We compose some condition on the rules that define predicates. So it must have only one constant, and this constant must allocate one of the parameters of the predicates. Predicates, and you can see at the end of the rule how the set variable is constructed. It's constructed with the set variable E that is either empty or equal to the variable allocated by the rule, and also by some of the set variables that are constructed by the predicate that are called by the rule. And to satisfy the predicate, we need that the structure satisfied some rule that is unfolded. So the satisfiability of the predicate is used by unfolding the predicate and satisfying the right side of the rule. So if we take back our example, we can now define this structure. So in view, we define a tree, a binary tree, such as the one we've seen in the class 5. Then in view, we define the list. And this difference is that we have at the end of the definition that all allocated variables are contained in the set variable. We compose the tree by using the overlaid starting convention, and we employ the tree structures share the same domain by using the same set variable in the predicate. So we can define local structure, for example, we can of list that we share some elements. And if we think of processing computer, they have balance that generates some properties, but they are also dictated linearly, so they are contained in a list that of execution. So we can describe such kind of structure. Now let's talk about the disability of the satisfiabilities. To the disability, we will use the satisfiability of the include a formula in set primitive decision definition to the satisfiability of the data formula. It's a good where the satisfiability is available. The reduction is done in several steps. So the first step is declare the predicate. So it's the notion that we introduce then in order to enable the special parts of the formula, we declare each predicates it fits some properties with the special parts. So I'm guessing which variables are allocated and which variable are added to some variable. Once we have declared all the predicates, we can define decorated rules for those predicates. To do so, we take the rules of the set of predicates and we construct all the decorated rules that we can, and we only keep coherent rules. So I will explain what is coherent later. Next, we want to deal with the cardinalities of the set variable. So we want to describe what are the possible cardinalities for the set variable. Also, we compute formula for each set variable. And finally, once we have done that, we take a decorated formula and a decorated set of negative function, and we translate it into a data formula to the negative function. Okay, so let's go a bit deeper in each step. So first, let's talk about decorations. So what is the decorated input? So we talk about the and we add these 4 elements. We have 2 sets, one set for describing the indices of the parameters that are allocated. One set for describing the indices of the elements that are added to the set variable. And 2 relations, one relation for the vaccine and one relation for the non-vaccine. So any total of 4 elements is a decoration. Now to do the same thing with formula. So we have a formula with predicates. We decorate all the predicates that give us the decorated formula. And we can just calculate equivalent of these elements to the formula to find some predicate what are the vaccine imposed by all the decoration formula, what are the vaccine, what variable is allocated, and what variable is set to given set variable. So now we declare the rules. So we take a rule on the left-hand side we have the predicates, on the right-hand side we have the formula. We declare the predicates, we declare the formula by declaring all the predicates of the formula. And if the element that we just define match, then we say that the rule is coherent. Then assume imposed on the left-hand side are imposed on the right-hand side. The parameters allocated on the left-hand side are also allocated on the right-hand side. So let's see an example. We take a formula, we take a 2 lists. We consider that there are non-empties that add all the elements to set variable. So here, the only possible equation that leads to coherent is this equation. As we only when we allocate the first parameters and we add it to the set variable, then both sets are integer only one, because x is the first particle. And there are no aliasing and no non-aliasing imposed by the rule. The aliasing is in P and the non-aliasing is the alteration. So we can only decorate the two predicate with this decoration in order to have a rule. All the other rules are insatisfiable, so we eliminate two of them. Now let's talk about cardinalities. So first, let's see an example of why it is useful to describe the cardinalities of the same variable. Once again, we have a list. So we have the first list that is given and the second list that is odd, and we add all the elements in the same variable. And we know, for example, to impose that the same variable are equal. So we can see that this is impossible. We can compose the two lists, but we cannot have same variable with at the same time cardinality odd and cardinality even. So we want to add formula to eliminate those kind of numbers. So to compute those formula, so for example, for the even list, we construct a grammar of cardinalities. So you can see that this grammar is just constructed by taking the rule and replacing the control by one. So it ends up constructing numbers in memory. So the language, these cardinalities are one number, and it corresponds exactly to all the possible values of the cardinality of the same variable. If we can create unfold the rule of predicates that create a list of certain number of elements, then we can use the same unfolding in the cardinality to construct the number in binary. And to construct the formula that describes this, we use the Barrett's image of the language. So Barrett's image is exactly the number described in the binary. And we can construct the formula in our time because it's basically the math. So for example, simplify this kind of formula. Therefore, we can see that the variable ix is associated to the set variable x can only be and unity because we have no entities. So now let's see the main translation. Again, we take an example. So this time we have two lists. They use the same key there. We suppose that we have one key and they add all the variable in the same variable, and we do what we have the same variable. So first, we want to translate the location variable, the small x, to a BAPA. So to do so, we create fresh BAPA set variable that corresponds to the location variable in the same direction logic, and we impose that the cardinality is 1. Next, we want to translate the predicate. So to translate the predicate, we associate the cardinality of the set variable with the amplitude variable. We use the formula that we just compute to describe what are the possible values for this amplitude variable, and we translate the condition imposed by the declaration to BAPA. So, for instance, if we remember that E and G only contain 1, then we know that x must be part of small x must be part of big x. So we impose that Vx is included in Vx. And we know that V is not ability to the same variable. So we impose that the corresponding variable is not from the same variable x. We do this for every predicate in the formula. Now, let's talk about the connective. So to translate the connective, we first translate the particle formula, so we just read for the predicates. And then we transfer the condition imposed by the connective. So the separating convention imposed that no variable can be allocated in both sides. So we compute a set that represent all the variables that are allocated in one side. So either allocated or location related to set variable. Then we impose like the three terms that can be the three sides on this one. For the overlaid separative connection, we do the same thing but field by field. So in our example, we impose as Vx and x must be destroyed by gy and y because they are allocated with the same field and composed with the overlaid separative convention. And finally, you can copy all the constraints, set constraint or arithmetic constraint directly to data. So we take data formula and we can decide in data if it is satisfiable, and we design it in order to like this data formula is satisfiable even if the correct formula is decided. So if you want to work with one implication is this design the data formula corresponds exactly to the constraint of the set formula. So if the set formula is satisfiable, we just hope that the structure we have and the data formula is satisfiable in the same equation. And on the other side, data construct associated location to all the variables. So basically construct the store and the set interpretation. And with this notation, we can reconstruct the if because we have the right constraint to data. So everything matches and we can reconstruct a if that satisfies the big formula. So to conclude, so our contribution is an extension of separation logic that handle overload data structure. We use the this diagram and we propose the procedure, the procedure for the satisfiability. What can we do later? So we are working on the containment panel because it's what is most useful in teaching. So we must impose all the constraints on the certificates and on the rules to bring the disability that we are implementing. And we can also investigate our procedure. For example, we don't know if complexity is type bound. We don't know if we must eliminate all the declaration. We can find a clever way to find a good declaration. And we don't know if all the conditions are needed. Some of the conditions that we impose are imposed in order to ensure the stability and the improvement, but maybe some can be relaxed just to keep the stability of the system. So thank you for your attention and questions.